Hello, I'm Sue Nelson and I'm inside Astrium UK's Andromeda clean room, the largest clean room at the satellite manufacturer's Stevenage site, and you'll find out why in just a moment. We'll also be hearing from a scientist who studies snow, and as fears of radioactive leaks in Japan continue, we hear about the ongoing monitoring of radioactivity in the UK after the Chernobyl nuclear accident 25 years ago.
It was actually monitored from a low-flying aircraft. It flew across the whole of Northern Ireland in tightly spaced flight lines just 200 metres apart. So it's the most detailed survey of cesium and largest survey of cesium ever to have been done.
The Andromeda Satellite Clean Room is a large and industrious space. It's about 50 metres square with quite a high ceiling, which is needed to get the length of the satellites in one of several pieces of scaffolding so that people can work on them. And it's extremely industrious because around me there are lots of people who are actually working on the aluminium structural panels for various telecommunications satellites. But the reason I'm here is because of a satellite that was built here that's part of a forthcoming European Space Agency mission to improve our knowledge of the Earth's interior and its climate. It will do this by examining the Earth's magnetic field, and it's an Earth Explorer mission called SWARM. With me is Dr. Ralph Cordy from Astrium UK's Division of Earth Observation Science. It's called SWARM. That's a bit of a hint, really, isn't it, about the nature of the satellite itself?
Well, that's right. As you can imagine, it's not just one satellite, it's in fact three.
Why do they need three satellites then?
Well, it's to do with disentangling different effects. It's to do with being able to separate effects that are changing with time and from ones which change with space. And it's felt that the simplest way to do that is to have a constellation, if you like, of three satellites.
I know that this satellite was put together here because about a year ago I was in this very clean room for another mission, and it stood out to me from the others because it didn't look like a typical washing machine square box, which is so often the phrase used for satellites because, let's face it, that's what they look like with a couple of solar panels on. This was tall, slim and pointed.
When you get used to the typical run of satellites coming through a factory like this, I think of the big telecommunications satellites as being like London buses. Well, for me, the SWARM satellites were like long, sleek, dark racing cars.
Why was it built in that particular way? Why does it physically look so different?
Well, I guess there are two principal reasons for that. One is the environment, the orbit that the satellites are going to go into. That's a relatively low orbit, and it means that they have to be sleek, very slim, to help reduce the pressure of the residual atmosphere at the height it's orbiting at. And the other reason is that it needs to keep its sensors, its extremely precise and sensitive magnetic sensors, as far away from any disturbance, electronic disturbance on the satellite as possible. And therefore it's very long and actually extends its length by a 4-metre long boom.
This 4-metre long boom then is the reason that it has been described as a giant mechanical rat, which, considering you and I both see it more as a sleek racing car, seems slightly unfair.
It does seem a bit unfair, but the tail of the rat, the boom if you like, is really very vital. It's on there that we support what's called a vector magnetometer, the really heart of each satellite, the device that is providing the very precise measurements, not just of the size, but of the very detailed direction of the magnetic field that each satellite is flying through.
Ralph Cordy, thank you. And we'll discuss the special ways that these satellites had to be put together because it's measuring the Earth's magnetic field a little later on in the podcast, as well as meeting Astrium UK engineer Julia Ryan. But first, our latest audio diary. If you've been following us on Facebook, you may have seen a beautiful picture we posted of ice-encrusted trees in northern Canada. It was taken by Mel Sandels from the National Centre for Earth Observation, who's been near the small town of Churchill to study snow.
Churchill, Manitoba in Canada. It's much milder than we expected. It's about minus 10 degrees, whereas the average mean temperature is around minus 23. So I'm here with colleagues from Environment Canada at Northumbria University, and we're here looking at how to measure snow mass using satellites. I was a bit surprised. I've been doing snow research for the last 10 years. I was very surprised at how white everything was, and my boss laughed when I told him this. But what I mean by white is that the sky is white, the ground is white, the trees are white. You can only just make out the outline of the branches. And I've got a colleague, Chris Dirksen, he's been coming here for the last 10 years, and he says he's never seen anything like it. He says it's like something out of Narnia. Okay, so my colleagues are about to carry out a snow depth survey, so they'll be shouting out snow depths at a 5 metre scale every metre, and I'll be writing down the measurements. Okay? 36 centimetres.
And 33.
33.
We're in Churchill because ultimately we'd like to be able to measure snow mass from satellites. Snow is incredibly important because approximately 1/6 of the world's population rely on meltwater from snow and glaciers for their water supply. So it would be really useful if we could measure this resource using space satellites, so we can measure it across the globe.
So Nick, we've just dug a 5 metre trench, and you're now brushing the trench face. Can you tell me why you're doing that?
Well, what we're trying to do is we're trying to get a trench face that has been undisturbed as possible by the cutting process. So when you do cut it, the teeth of the saws and the objects that you use put in some artificial variability to the trench surface. So in essence what we're trying to do is we're just trying to smooth those out, trying to remove those. So what we try and see is what was there originally before we started cutting into it.
I guess most people think that snow is white and that's all there is to know about snow, whereas in fact it's a very interesting material. As soon as snow falls on the ground, it changes depending on the temperature conditions around it and things like wind speed. You can start off with the stellar snow crystals that everyone thinks of, the typical pretty pictures of snowflakes, but as soon as they land on the ground, they change very quickly. Some of their arms break off, they become more rounded, and they tend to form little spheres or ball shapes, which can be either bonded together in great huge chains of balls, or they can be separate.
Chris Dirksen from Environment Canada is about to have a look at the snow face. Chris, can you tell us what you can see?
Well, we can see a number of layers in the snow. The total snow depth here is about 40 centimetres. And we can clearly see at the top some fresh snow that has fallen over the past 24 hours or so. And then all the older snow layers are beneath that. And essentially the grains get larger as you move down to the bottom of the snow. And if you use a few very simple tools, it's possible to mark out the thickness of each layer.
There are two different ways of measuring snow mass. One uses radiometers. They measure passive microwave radiation. In a similar way to the Earth emits heat, the Earth also emits microwave radiation. So we can use radiometers to measure these. And this is where my work is focused on. But you can also use what's called active sensors. They're radars that ping a microwave signal into the snow, and the proportion of signal that comes back is related to the snow mass. By using these scatterometers, you can get an estimate of the snow mass.
Hey, what's the height?
32 plus 134. Thanks. Same as the last one.
So let me introduce you to Josh King, who's from the University of Waterloo. Josh has been making some scatterometer measurements at our field site in Churchill. Josh, can you tell me a bit more about a scatterometer?
Scatterometer is a type of radar unit that we use to direct microwaves towards the snowpack. We measure the response from that, and hopefully we can extract some useful information from the snow based upon that response.
So what sort of information do you hope to get from the snow?
Well, we're hoping to find certain parameters such as the density of the snow, the size of the grains, and potentially the amount of water that's stored in that snowpack.
So why do we care about the amount of water stored in the snowpack?
Well, from a global context, it's a very important solid-state storage point of fresh water. So if we can find ways to figure out how much water is stored globally, we can make better choices and better informed decisions as to how to use water, where it goes, and why it goes places.
I understand you're also involved in a project called Snow Tweets. What's Snow Tweets?
Snow Tweets is a new type of project which we like to call crowdsourcing, or citizen science, where we allow the general public to be involved with science by submitting information to us through means such as Twitter. So the idea behind Snow Tweets is that any person can go out in their backyard, or wherever they are, put a ruler into the snow, measure the depth, and then use Twitter to send that information to us.
So how do you use all that information that people are submitting to you?
The information goes towards things such as validating models, or checking to see if other products such as snow coverage or snow depth that we've estimated from satellite sensors is correct.
So we've come to the forest site today. We're halfway through all our trench measurements. Nick and Josh have gone up in the Skyjack to have a look above the forest canopy and look down and see the snow around them. Skyjack is basically a platform that lifts up about 9 metres, but it's pretty rocky in the wind and swaying. Now it's cold today, much colder than it has been. I can feel ice crystals forming in my nostrils and my hair stuck to my eyelashes. Just now I'm about to go up in the Skyjack myself, which is very exciting.
Mel Sandel's audio diary from Churchill in northern Canada. We're expecting more from Mel in the coming weeks, and we've also given audio recorders to scientists studying whales in California, high seas in Antarctica, and a couple more are about to head off to the Arctic. You're listening to the Planet Earth podcast. It's a tragic coincidence, but as the investigation starts into the radiation leak at the damaged nuclear plant in Japan, this month also marks the 25th anniversary of the Chernobyl nuclear disaster. On the 26th of April 1986, an explosion in reactor number 4 at Chernobyl sent a cloud of radioactive debris into the atmosphere. The disaster killed at least 30 people, but thousands have since died prematurely, and tens of thousands of people continue to suffer the effects of radiation. But the impact wasn't only confined to the area immediately surrounding the plant. Richard Hollingham's been speaking to geochemist Kathy Shive from the British Geological Survey, author of a recently published study of Northern Ireland.
Around 60% of the material ejected from the reactor fell within 20 kilometres of the site. The material that went higher into the atmosphere was carried in a radioactive cloud, and it split into about 3 portions which spread across most of Europe.
Let's go to your research then. You were looking at the radioactivity from Chernobyl 20 years after the accident.
Yes, there's still a lot of that radioactivity still in the environment. We were just looking specifically at a radioactive type of cesium called cesium-137. It has a half-life of 30 years, so that means in a period of 30 years, half of it will decay away.
And how did you do this?
It was actually monitored from a low-flying aircraft. It flew across the whole of Northern Ireland in tightly spaced flight lines, just 200 metres apart. So it's the most detailed survey of cesium and largest survey of cesium ever to have been done.
So when you say you went in these flight lines, that was almost, I suppose, like mowing a lawn. So you went backwards and forwards right across Northern Ireland.
Yes, it was like mowing a lawn, and it took 2 years. And the actual distance that the aircraft flew was equivalent to flying twice around the globe. So it's such a detailed survey over a relatively small country.
Now, we've got various maps spread out across the table here, and this map shows the results of your survey. It's a bit like a geology map in that it's multicoloured. You've got a spectrum of blue through to red here in patches across the map. What are we looking at? What do these colours represent?
The colder colours, the blue colours, represent the low activities of cesium-137, the radioactive type of cesium that we studied. The pinks and the darker colours represent the higher activities. And they are in very, very detailed national scale bands across the country. If you can imagine looking at a clock, one of the biggest bands is at 5 to 5, if you can imagine, and there's another banding system going across the country at about 10 to 4, if you can imagine.
So if we look at this particular strip of red that runs across slightly diagonally from the bottom right to the top left, right away across Northern Ireland, how come you would get a band like that of this radioactive isotope?
True, there is a big band of higher activities going from the Mourne Mountains in the south across up to the Sperrin Mountains in the north. This represents, we think, where the cesium was washed out of the rain when the Chernobyl plume passed over Northern Ireland.
Is it dangerous?
No, the levels are at low environmental levels, but it's interesting because it does show us how the plume behaved, how the cloud of radioactivity behaved, and how it is still in the environment today.
So how can you use this information?
Well, interestingly, cesium-137 used to be used to measure how soil moved around the environment, how it erodes. But because the distribution from Chernobyl is much more patchy, we can't actually use it now to trace how soil moves.
And presumably this is also useful if, heaven forbid, there was another nuclear accident or someone tested a nuclear weapon in the atmosphere.
Yes, we do understand much better how the material moves and how that meteorological models or weather models are incredibly important for tracking where the radioactivity goes and how it behaves. But this specific research that we have done has shown exactly how detailed and how closely correlated the deposition is to rainfall. In other words, that the rainfall washes the cesium out and it basically sticks there where it lands.
Kathy Scheib from the British Geological Survey on the long-term legacy of Chernobyl. And as you may know, Richard recently visited Chernobyl for the BBC World Service. You can see a picture of him in his protective equipment on our Facebook page. To find our Facebook page and the Planet Earth Online website, put Planet Earth Online into any search engine. And there should also be some pictures of the clean room, where I am now at Astrium UK in Stevenage with Julia Ryan and Ralph Cordy. Ralph, about the swarm mission, which is why we're here, because we're in the very clean room that these 3 satellites were built. But because they're measuring the Earth's magnetic field, that made the construction slightly different to how you would normally make a spacecraft.
We've had to be careful in every way we've been working, in our choice of materials for these satellites and in the techniques we use. For example, we've got to be careful that nothing that we use is going to generate its own disturbing magnetic field. We can't leave any residual magnetism in the structure that is going to distort the measurements that we will make in space. So the materials we choose, far from being the typical materials we would use for a telecommunications satellite, we've had to build these out of carbon-reinforced plastic. We've had to use ceramic materials to form a kind of optical bench on which to support the vector magnetometer. The tools that we use to do work on the satellite, we've had to make sure that those contain no residual magnetism themselves.
Julia Ryan, you worked on the assembly, integration and testing part of the campaign for the Swarm satellite. What sort of testing did it involve?
The most environmentally disturbing part of a satellite's life cycle is the launch, because being on top of the rocket, it gets shaken around a lot and subjected to a lot of noise. In order to make sure that it can survive that, we have to do simulations on the ground using computers and then test it afterwards.
Often all the components of a satellite aren't put together until launch. So how do you test a satellite when it perhaps doesn't have all the instruments on board? So will be slightly different in weight as other characteristics.
Well, when we're testing the structure, we use mass dummies to represent the different instruments on board. So these will be blocks of typically sort of metal or plastic to represent the general size and weight of each instrument. And these bolt into the same inserts that we would bolt the actual equipments into, and it gives a representative mass and a dynamic response of the spacecraft when we test it.
You mentioned metal there. Did the metals and the choice of metals on the spacecraft itself have to be very particular to avoid the induction of magnetism, which would then You don't want that because it would affect the instruments and what they're trying to measure.
Yes, that's right. All of the metal components of the structure, for example, the brackets and the fasteners themselves, all had to be made out of titanium, whereas we would normally use perhaps aluminium or sometimes even stainless steel. These parts were made out of titanium to reduce the magnetic effects.
Ralph, the 3 swarm satellites are due for launch next year. Will they be launched in stages?
No, in fact, they're going to be launched all together from one rocket from northern Russia, and they're going to be put together into an orbit over the Earth's poles, very close to the Earth's poles. 2 of them at a slightly lower altitude, flying almost in tandem, almost side by side, in fact, around the Earth, with the other one a little bit higher and slowly drifting away over time to separate them in time and space from each other.
Ralph Cordy and Julia Ryan, thank you very much indeed. And no doubt we will report on the measurements of the Earth's magnetic field in more detail after the swarm satellites have launched.